Good afternoon. Welcome to lectures 87 and 88. 87 and 88 today on thermodynamics of materials. We will continue with the solution thermodynamics. So we are discussing. We have discussed last day mixing functions. Okay, and we have discussed at length. Today we will give you phase diagrams which are in agreement with this behavior of solutions, like ideal solution or non-ideal solution with positive deviation or negative deviation. So start. So what should be the corresponding? So let us give a caption to this. The caption will be important. So different types of 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 binary phase diagram. Binary phase diagram. अच्छा, different types of binary phase diagram. Phase diagram showing ideality means ideal solution, or ideality and non-ideal, okay, or non-ideality or non-ideality or non-ideality in liquid and solid solutions, okay, liquid and solid solutions. Solid solutions. This is our this is the subtopic. Topic is solution thermodynamics continued, and this is the subtopic. So first, A, the isomorphous system. Isomorphous system. What is the characteristics? I will give you the characteristics. Liquid solution, Okay, let me draw this right hand side. Draw this diagram. Temperature on the y-axis, mole fraction of B in the binary system AB, 0 to 1 here. 0 means mole fraction, xb is 0 means xa is 1 and xp is 1 means it is pure B. This is pure A. And what is this? This is the liquid solution, liquid phase. This is the alpha phase solid solution. This is liquid solution, you may write, okay. Alpha is the solid solution. You may write here solid solution. This is liquid solution. Okay, this is the isomorphous system. So we can write this characteristic liquid solution, which is liquid L, is ideal behavior, ideal solution, ideal, ideal, ideal solution. Solid solution, solid phase, solid solution. What is this? Alpha is also ideal behavior. What happens when this okay, actually when both are ideal, there are other characteristics are what? This, there is no ordering in the solution, in solution of AB. There is no ordering, okay, with respect to A and B. There is no order arrangement of A and B. It is totally random. So we actually write this liquid solution, this, okay, and then what else? Liquid solution, just these are the properties as it. No ordering, no ordering of ordering, no order in arrangement of A and B. No order in the arrangement, in the arrangement, in the arrangement of A and B in either liquid and solid solution. This means no order means this is actually random distribution of A and B, A and B. Oh, sorry. Oh, this is actually A and B, random distribution of A and B in liquid and solid solutions. Okay, it's okay. So this is figure 1. This is figure. What happens? Figure 1. Figure 1. Okay. B. This is figure 1. Okay, right here. Figure 1. Second is what? Or you may give this 1. Figure 1. 1 may be better. Second is 2 is what? Eutectic phase diagram. Second is eutectic diagram. Eutectic diagram with limited solubilities. With limited solubility of A in B or B in A being A in solid solution of A in B and B in A, okay, in solid state, in solid phase. What is the diagram like? This is figure 2 right here. Figure 2, which I will draw now. What is this? Acha, let me draw first. Again, you have temperature, you have xb moving from 0 to 1. As you know, it is A, pure A. This is pure B, and the diagram will be like this. So what is this? This is again liquid solution, which will, this is the alpha phase, limited solubility of B in A. Is A enriched phase? This is the beta phase. As you know, this you have already read in physical metallurgy. This is alpha plus beta, liquid plus alpha. This is liquid plus beta. This is the, so what are the, when we come across this diagram, what are the thermodynamic interpretation or thermodynamic origin of this? Okay, what is the thermodynamic factor, thermodynamic, okay, what are the thermodynamic properties of the solution in this case? So liquid solution, write once more, liquid solution, which we say written L, is ideal, we consider ideal, and solid solution non-ideal, non-ideal with, non-ideal means either positive deviation or negative deviation. So with limited positive deviation. Let's check with solution with limited positive deviation. Limited positive deviation. Result of which is what? What would happen for this? Clustering. Cluster of A and cluster of B. This is A enriched, and this is B enriched. So cluster, clustering, and still another is what? Still another is what? As a result, phase separation. Phase separation. Alpha and beta. Okay. So this is second one. This is figure 2. Figure 2. Third. Next is eutectic diagram with eutectic diagram with no solubility between A and B no solid solubility between A and B in solid state. In solid state, so what is the thermodynamic here? What is this? Here positive deviation or here limited positive deviation, extreme positive deviation. Extreme positive deviation. So let me write here extreme positive deviation, because I have to draw the figure alongside. So let me draw the, this is figure 3. Figure 3. Draw this. This is very common diagram. Okay. Hang on. This is a liquid phase. Liquid plus no solubility, so pure A. This is liquid plus pure B. This is A plus B. No alpha, no beta. So liquid A. Okay. Another thing, it is the temperature. Is again as before Xp 0 to 1. This is pure A. This is pure B. Here I tell you what, I have actually forgotten to give you these examples. I want to give some examples here, so that will be helpful. So where shall I write? Where shall I write? Actually, I write from the bottom. Actually, example I am giving here. Example, which type of system? Aluminum, germanium system. What is example for this? Example for the second one. Here, right? Example. Example, I don't have space here. Example is what? Eutectic diagram, limited solubility, you know, iron carbon, but there are others also. Is this some actually aluminum magnesium, and copper silver. There are others also, but these 3 I gave you here. What is this? For this example, right here, example, copper nickel, FuMNO to great extent. FuMNO, these are oxide phase, though slag phase or oxide phase. This is the metallic phase. These 2 examples. Okay, so 3 is yes, properties. Properties example I have given first. Example, okay, example here. Example. Okay, example. Achha, let me first. Okay, I'll keep, sorry. I'll give you the first of all properties. Properties as right. Liquid solution L, still ideal. Solid solution positive deviation. Solid solution is what? Positive deviation and extreme, as I have already mentioned here. What else? This actually, so these two characters, these 2 properties we have mentioned here. Example here, I am giving example here. Example, what system? Aluminum, germanium. last but one, fourth is actually what you will have to consider is phase diagram. Phase diagram showing, this figure is what figure? Figure 3, figure 3. This is figure 3. Phase diagram showing intermediate compound formation. Compound formation. I'll give the properties here, but let me draw the diagram first. Let me complete this. Actually, this is a vertical compound. Oh, This is as before xb, sorry, xb moving from 0 to 1, namely A, B, your, and this is I should little bit lower it. Right here, this is AB compound. This is AB stoichiometric compound. So right here xb. xb is moving from 0 to 1, as you understand. This is the temperature axis moving up. This is your liquid phase as before. This will be what? Liquid plus A. This will be liquid plus AB. This will also be liquid plus AB. This will be liquid plus B. This will be what? A plus AB. This will be AB plus B, and AB is the compound formed. AB is actual mole fraction in AB is 0.5. So it is actually at this value. Let us better I write somewhere 0.5. Sorry, 0.5. Then it will be called AB. If it is AB2, so it will be actually mole fraction will be 2/3, 0.67. Or say A2B, then it will be 0.33B, XB. So XB. Scale is XB moving from 0 to 1, as you have seen all these cases. So what are the characters here? Liquid, solution L, still ideal, solid solution, is what? Extreme negative deviation. This is extreme positive deviation. This is negative deviation. That's why compound forms negative deviation. So negative deviation, extreme. This will be compound. Okay, if the negative deviation is less, then you have a phase, intermediate phase, the gamma phase. Okay, which is not stoichiometric compound, which have a range of composition. But this I am not considering. I am not teaching you phase diagram. I am showing you the connection between thermodynamics and phase diagram. This is okay. This may help you okay to understand the importance of thermodynamics in phase diagram. Next is what I have to say: liquid solution, solid solution, etc., etc. I think yes, here see opposite. You have just no order, complete ordering, order structure. Order structure, B around A around B. Okay, example sodium chloride. One sodium atom surrounded by 6 chlorine, and each chlorine again surrounded by 6 sodium. Sodium chloride is a stoichiometric compound. So it is a ordered ordered arrangement of A and B in solid state of A and B. Wait a bit, let me check actually. I have to. Acha. Complete ordering as a result, compound formation. Ordering and compound AB formation. AB formation in solid state. We call it intermediate phase. Intermediate phase in the solid state. Solid state. So we are through with this. This is figure what? Right, figure 4. This is also figure 4. Last one actually I have to remove this. Remove this figure. I'll actually remove this part, this one, first one. First one I remove. First one. Fifth one. Fifth. Monotectic phase diagram. In which both liquid and solid solution show positive deviation. So you can write this. So let me draw this. So that will be interesting. Draw this diagram. This is what? Here positive deviation in liquid phase means there is phase separation in the liquid phase. This is the first time we come across. So two liquids will be shown, liquid 1, liquid 2. Oh, okay. And this is liquid 1 plus liquid 2, like alpha plus beta, liquid 1 plus liquid 2 in the liquid solution. So what is this? This is your alpha phase. And what is this? Let me write liquid 1, oh sorry, sorry, okay, later on. Temperature, okay, XB as before, 0 to 1, this is pure A, pure B, okay. Now label this. This is your alpha phase, this is your beta phase. This is what? This is what? This is what? Liquid 1 plus alpha. This is what? I am very sorry. I am very sorry. This is a mistake. Yes. This is beta phase. And this is what? Liquid 2 plus liquid 2 plus beta. Liquid, how does it look like? Clear? Clear. Okay, thank you. Liquid 2 plus, this is what? Right. Liquid 2 plus beta. So what is this here? Liquid 1 plus alpha. So what is this? What you get here? This is liquid plus alpha. This is liquid 1 plus liquid 2. So alpha plus liquid 2 from liquid 1. This is monotectic reaction or monotectic transformation. I would prefer monotectic transformation. This is alpha and this is obviously alpha plus beta. Alpha plus beta. So this is your monotectic point, like eutectic point, eutectic temperature. So monotectic point, monotectic temperature, monotectic transformation. What is the monotectic transformation? I am writing. Before this, let me write here the properties as before, right? Is what? So I write here, as I have already shown, liquid. Actually, by the way, above this point, as temperature increases, positive deviation decreases. That I will show you today. So there is no deviation anymore. This is ideal behavior. And this is, there is no phase separation above this. At the top of this, okay, this is above this, okay, maximum point. This, there is no phase separation. As temperature decreases, phase separation starts. Phase deviation decreases. Extent of deviation decreases as temperature increases. This actually I will show today. So after this, no deviation. So it tends to be ideal solution. So single phase. That's why single phase. Above this, only liquid. At the top of the dome, liquid, only liquid. Okay, careful. So liquid, what shall I write anyway? To cover this feature, liquid, say L. This is the two phase liquid. Okay, liquid 1 plus liquid 2 is positive deviation. Then you have solid. What you have? Alpha plus beta, positive deviation. And in passing, note this, that what is the monotectic transformation? monotectic transformation. What is this? See here, this is the point. Like exactly like this. What is this? Liquid goes to A plus B. Or here, liquid goes to alpha plus beta. Here, liquid 1 goes to what? Alpha. Liquid 1 plus alpha means alpha, and this side liquid 2. So this is the monotectic reaction or transformation. Liquid 2, let me write alpha first. Alpha first, liquid 1 plus alpha, this side alpha, that side liquid 2. So difference between eutectic transformation and monotectic transformation is this. Here actually solid phases, actually you get from the liquid you get 2 liquid phases involved. 2 liquid phases involved. Here only one. Liquid goes to A plus B or liquid goes to alpha plus beta. So with this we have completed this topic 5 right here. Figure 5 shall I have written? Figure 4, oh yeah, figure 5, and this is also right here. Figure 5, oh right here, figure 5, okay, and just keep example on the left. What are the examples of this? Iron tin, very popular, iron, lead, then also few more I am giving you, that is aluminum, indium, and also I give silver, nickel. This is the examples that I gave you. This is lead. Make no mistake, lead. Thank you. This topic is over. I will pick up now the next topic, which is actually a review. Or let me explain this. So, can I remove all these things now? Remove this. So, remove this. Very good. So, next topic, I would say, this is, we will once again pick up this 3, for some reason, 3 different spontaneity criteria and their application domains This is the topic. I want to uh, finish this discussion, which I have done twice before, but in each case there was audio problem. So that's why I took I take up this once more, and last time, and also removing any confusion that was still there, and if anything was missing for the audio labs. So review Second time I am reviewing this. Review once more to make up for the interruption in the audio interruption in one or two previous videos. Previous classes. So this is the start. Three different spontaneity criteria. One is delta G less than 0 is the first one. The second one is right here, right there. Second one is delta G prime. If you have still any doubt, you can clarify today. Delta G prime PT, which we actually commonly write, consider delta G PT. Okay, this is a matter of symbol and okay, this is in short. Delta G PT is actually means this is less than 0 second. Third is what? Remember, spontaneity only, not equilibrium or impossibility. If it is equilibrium, it will be 0 also. For equilibrium is 0. Here also 0 equilibrium. This is spontaneity only. Third is delta S universe greater than 0. Universe greater than 0. We will discuss these three criteria and okay, show you and give you the limitations of this criterion or generality of this criterion. Okay, particularly universal acceptance of this criterion. I explain this. Criterion 1, which is delta G less than 0. Just revise what you learned before. It will help you. Applies to, I discussed this, but there are some audio difficulties. Applies to examine. It is better. Examine whether a given chemical reaction, reaction given chemical, e.g. I have to write this, e.g. A plus 2B goes to 3C is spontaneous at a given state of the system. At a given state of the system. Given state of the system. E.g. for example, e.g. what is the state is given by composition, temperature, pressure, say 50% A, mole percent or mole fraction 0.5, 30% B, 20% C. This part is composition, and then you have to give temperature and pressure. Then it is state is fully defined. Given this at this stage, here note here at a given state, so here not two states involved. Here two states are not involved. Okay, where here two states are not involved. Important, are not involved. The criteria about a single state are not involved. Okay, yet delta G is delta G, which must be a change in in free energy applies to the given state given single state. Single you can write just in addition, you just okay emphasize this, it is single state. Here delta G is as delta G is what is the delta G? Must be a change, but one state, single state, not two states, as we are used to. So with saying what it will be? It will be is sigma G. It is about product and reactant comparison. So G products minus sigma G reactants. Well, about that state, only one state involved at the given state. Sigma G at the given state under study. At the state under study. Just write extra. This may be a little bit okay, is superfluous, but at the state, but not bad. It will clarify your confusion, if any, under study. It is what it will be, you know very well, that is 3 Gc bar. In the present case, it will be 3 Gc bar minus Ga bar plus 2 Gb bar. You may recall also, what is this? Recall, what is Gi bar? Gi bar is Gi0 plus R3 ln Ai. Okay, this and here. The generality of this criterion is that the generality of this criterion is that it is not limited to any particular process, to any particular condition, particular condition under which the under which the chemical reaction is carried out. Chemical reaction carried out. E.g., it can equally apply to a constant pressure, constant temperature, to a constant temperature, constant pressure process. B, constant temperature, constant volume process. C, constant internal energy, constant volume process, which we know as isolated system. Isolated system. Actually, isolated system is what? A constant internal energy, constant volume system, but with no non-mechanical work, like electrochemical work or surface work. But since these are not considered, okay, in our case, okay, only chemical reaction. So these two are enough to define an isolated system. So this is okay, isolated system, and so on and so forth, etc. Any other combination you can consider, etc., etc. So, right. The limitations, as long as, etc., as long as, as long as, as long as, but you may consider constant temperature, constant volume, isolated system, no problem. But as long as temperature, pressure, and the composition, as long as the temperature, pressure, the temperature, pressure, is a temperature, pressure, and composition. Temperature, pressure, and composition. Temperature, pressure, and pressure and temperature, pressure, and composition of the state under study is known. Okay. Then a limitation of this criterion, the limitation, it looks like general here, but there is limitation. The limitation means you cannot apply this criterion. Where the limitation of this criterion is that it is not applicable to, it is not applicable to a fixed mass, fixed mass, fixed composition system. Fixed composition system, e.g. N moles of an ideal gas. N moles of an ideal gas undergoing isothermal expansion. Just for example, it can be isothermal compression also, or it may be an adiabatic process also, but with N moles of ideal gas, which is fixed mass, fixed composition, undergoing an isothermal expansion. The appropriate criteria. Now, what is the criteria in this case for spontaneity or irreversibility? The appropriate criteria for spontaneity for this situation is given below in criterion 3 below in criterion 3 when I will discuss this. So next will be criterion 2. So let us remove this. I think we can remove this criterion 2. Can I remove this? I think I can remove few lines. Okay, here, since actually I don't have criterion 2. What is this? Delta G prime PT, which is commonly taken as delta G PT is less than 0. Okay, so this here is 0, less than 0, applies to examine to examine whether the passage of a chemical reaction system, whether the passage of a chemical reaction system e.g. A plus 2B goes to 3C under constant temperature, constant pressure, or a not only chemical reaction system but solution system also, or a solution system. In both cases we will use this criterion. I will explain more. Or a solution system or a solution system or a solution system e.g. the one that we are discussing often, N moles of A pure plus Nb moles of B pure goes to under constant temperature pressure, as you know, as you often write, and also you know this is a mixing process, is Na plus Nb moles of Ab solution. So, or a solution system A plus B solution, okay, you can write Eg, I started bracket here, so you must get another bracket here. Eg solution system from state 1 to passage of the reaction system of solution from state 1 to initial state to final state. In state 1 to state 2, note, two states are involved. Note, two states are involved. As we know, delta G between state 1 to state 2, note two states are involved. Note two states are involved is spontaneous. So we will examine whether the passage from state 1 to state 2 is spontaneous through this criterion of spontaneity, is spontaneous. Is spontaneous. State 2 will be, it may be noted here, and you know very well, this state 2 will be, recall my discussions and the plots. State 2 must be any state between state 1 and the equilibrium state. Inclusive means equilibrium state will be included up to equilibrium state. That is state 2 must not be a post equilibrium state. This I discussed, okay. In solution, it is also initial state, non-equilibrium state. This is the final state, equilibrium state. So up to equilibrium state, we can use this criterion, and we have already used. So let us see what we may consider further. The limitation of this criterion is that the great limitation is that the process must be carried out under constant pressure and constant temperature. Carried out under constant pressure and constant temperature. Under constant and constant pressure P and constant T. we have already used this criterion. Where? Twice we have. One is already delta Gm mixing is spontaneous process. This is actually delta G prime. I'm showing you. I've already shown you. And another is also a chemical reaction that I will refer to now. We have already applied this criterion to the to the preceding solution system. Preceding solution system to prove that mixing is a spontaneous process. To prove that mixing is a spontaneous process. Mixing is a spontaneous process. Already recall this delta Gm prime all negative. Okay, this we are under constant pressure temperature process. This one we have shown this. Mixing is spontaneous process, and also to the this is not only here, and sorry, and also to solution system as well as chemical reaction system, and also to the a also to the chemical reaction system taken up recall this taken up in lecture 70, assignment number 7, assignment number 7 disturb is there any disturbance here? No, it's okay. Lecture 7 70 I'm checking. Assignment number sorry assignment number In assignment number 7, problem 6. Problem 6. What is the problem like? I am also giving the starting point. Problem 6. Consider consider this problem. Consider so that you can easily find the problem or remember it. Consider the following hypothetical process. Consider the following hypothetical process 70. Hypothetical process in a closed system. Process, what is this? A closed system contains initially one mole of CO, 1 mole of CO at 1000 Kelvin and 1 atmosphere. And I don't want to write it. This is you will get this in the assignment. This problem, actually this was about dissociation of carbon monoxide into carbon dioxide and carbon. CO, twice CO goes to CO2 plus C. That problem. There we use this, okay, you get back and you will find this. The application of this two applications, one in solution system, another is chemical reaction system. So this is over about this. And then criterion 3, and the last one, then we will be over. Criterion 3. What is this? Delta S universe for spontaneity. We are considering for spontaneity. Yes, spontaneity. Different spontaneity criteria. Delta S universe greater than 0. Okay. So which is the original second law statement? Second law statement. Original second law statement. So is universally applicable is universally underline. Actually, you underline here also spontaneity. Actually, we are considering spontaneity. If you want to bring in equilibrium criterion, it will be 0. 0 here, 0 there, 0 there. Okay. Is universally applicable to any system any processes, any systems, any processes. no barrier, everywhere you can apply this. For example, these criteria will be applicable to find the spontaneity, that is irreversibility, to find the spontaneity and irreversibility, are synonymous in the sense they are not reversible. Or irreversibility. Recall that definition: spontaneity is when the system moves from a non-equilibrium state to an equilibrium state through a continuum of non-equilibrium state, through non-equilibrium states. So, our passage from spontaneous process is the passage of the system from a non-equilibrium state to equilibrium state through non-equilibrium states. And what is the irreversible process is similar, is the passage of the system from a equilibrium state, starting point is equilibrium state, to another equilibrium state through non-equilibrium state. Like irreversible expansion of ideal gas, initial state equilibrium and final state also equilibrium, or through non-equilibrium states if it is irreversible expansion. So that we are considering, or irreversibility. Note that this or irreversibility of the isothermal expansion acha. Let us do one thing. I think it is better we remove this part. This part is no longer required. Over this have been discussed. So no point in retaining these lines. So let us continue from here. Expansion, you start here. So of the isothermal expansion star. Isothermal expansion, what is this? With pressure and volume changing. Recall this: with pressure and volume changing, pressure and so isothermal process for ideal gas, pressure volume changing. Remember P1 V1 T to P2 V2 T, P1 V1 T to P2 V2 T, initial state, final state. So this was for this. Remember, for this, to show that it is irreversible process, to prove that it is an irreversible process, the criterion for irreversibility will only be obtained from neither from this nor from that, only this. And this is all most general, universal. You can apply to any situation. So this situation you cannot apply this to. So the last resort is this, and this will give you that this is that the delta S universe is positive and the process is irreversible. So this this was already shown. Okay, when you considering ideal gas as the system, and different type of processes with n moles of ideal gas, constant constant temperature, constant pressure, constant volume, and adiabatic. 4. With pressure and volume changing, pressure volume changing of n moles of ideal gas. The isothermal expansion of n moles of ideal gas, n moles of ideal gas, n moles. It may be noted in passing that for the reversible isothermal expansion, reversible isothermal expansion of n moles of ideal gas. What is that value? What is the delta S universe? Will it be greater than 0 this time? No, this will be 0. One is equals to 0, another is greater than 0, and when it is less than 0, it is impossible. Remember this. Remember all these things. Okay, so this part is what? Another important example, which is the concluding one, last one. Another important example is the demonstration that mixing is a spontaneous process. Recall, you have already proved through this criterion, already proved. I have shown. One thing I missed, that in terms of entropy also, this criterion can also be used. I forgot. In fact, today this is the first time I am showing you. So both are possible, and you will be more satisfied. Let us see how, because this is general, will be applicable everywhere. So let us see. It can be applied to the mixing process. So this is the mixing. For this purpose, wait a bit. Give a rest. Give this rest and take a new one. For this purpose, let us rewrite rather. Let us rewrite the mixing process previously considered for 1 mole of not Na plus Nb moles, but for 1 mole. Okay, it is nothing but actually you have to divide by Na plus Nb for 1 mole instead of intensively for 1 mole of the solution or 1 mole of the solution. What type of solution? We consider ideal solution. Ideal solution. Just I will demonstrate this. Okay, let us see. So let me write this. So what shall I write? What is the let us rewrite. So let us rewrite. Let us rewrite. X since 1 mole total, we have to consider X moles means X moles of A and XB moles of B. So and they together is Xa plus XB, which is 1. So mole Xa moles means Xa is the mole fraction, but here considering as Xa mole, that mole fraction number of moles we are considering Xa moles of A pure as before. Instead of Na, I am writing Xa. Previously for Na plus Nb moles, I am writing for 1 mole. So same thing, no problem. It's no problem. Xa moles of A pure plus Xb moles of B pure. Again, as you know, it is undergoing a mixing process under constant temperature, constant pressure, mixing, giving you Xa plus Xb moles of Xa plus Xb moles of moles. It is actually not moles. Actually, Xa cannot be is less than 1, so it is mole fraction. Xa plus Xb mole. Xa plus Xb mole of AB solution. What is the nature of the solution? Ideal nature. This I have already mentioned here. Solution, ideal solution. So this is the process. So now we actually have to find delta S universe. You know, note here. Note Xa plus Xb is how much? As we know, mole fraction sum to 1 always. Okay, so we have considering 1 mole solution. So delta Sm. So what is delta S universe? We will find and we will show that it is greater than 0. So first what we will consider delta S system, then delta S surrounding, and then delta S universe, which is the sum of delta S system and delta S surrounding. Start delta S system. Delta S system is what? It is mixing process. Delta S system. You see, remember, is delta Sm Pt. Delta Sm Pt. And remember, ideal solution. Ideal. We call this. We call delta Sm ideal. It is actually integral molar. M for mixing. Integral molar entropy of mixing. Ideal solution in the ideal solution case, and we have considered ideal solution. This value already there. Last class is what? Last class, okay? Is what? Remember? To remember this, tell me. Minus R Xa ln Xa bracket, first bracket only, Xa ln Xa plus Xp ln Xb. Delta system, this is also constant pressure, this value. This is delta system actually. This I said number of times, this delta system. And what is this value? Tell me, remember, is positive. Why? Xa, Xb both less than 1. So no problem. Now next is delta surrounding. Let me check if I have missed any point. Is positive, is okay. Delta surrounding. Delta surrounding I taught you when I was discussing systems are entropy chapter, remember, Okay, delta system and delta surrounding for this. I gave you a general recipe for delta system and delta surrounding. Delta surrounding is what? Tell me. Minus Q process by T surrounding. You look back and you will get this. Is minus, what is this? Q process is delta H under what condition it is true? Under constant pressure. Recall Q is delta H. And what is this delta H? Like delta S, delta H system is like this, delta S, this delta H is also write this. This delta H is actually mixing process. What you write? Delta H like this. Delta HM ideal PT by T surrounding with negative sign missed out. What is this value? What is the value of the numerator? For ideal solution, what is the enthalpy of mixing? 0. 0 minus 0 by T surrounding is 0. So last line, delta S universe let me check if it is okay. Anything missed out? No, nothing. Is delta S system plus delta S surrounding is positive value for system plus 0 value for surrounding is positive, means greater than 0. That is greater than 0. So is all over. This topic is completely covered and exhausted, and I hope you will have no problem. Okay, just go through this and check if you have any difficulties, and in that case I will once more discuss this. Next is so we have actually now the time to quit this part. This mixing property, and see mixing is considered here also. So 3 different criteria. I am sorry, I have to quit this, and I hope I don't have to repeat anymore, review anymore. Just this is final discussion and explanation and interpretation and applications, whatever you call it. So next topic, the one that I told you that I'll start quickly is excess functions. Solution thermodynamics continued. Excess functions, like mixing functions. Today is excess functions. Excess functions. Start. What is this? Start like this. GI bar excess. Start. I'll explain everything. Is what GI bar excess is? Is what I'll tell you. Is GI bar real solution? The solution under study you may call it, minus GI bar ideal. Well, ideal. Okay. What is this GI bar excess? Let me write the same way. GI bar M. Partial molar free energy of mixing, partial molar excess free energy. So write this partial because this bar is there. Partial. So it is A. So for A you are considering. So it will be partial. There is B also. Binary system B also. So A, when you are considering A, it is partial. Partial molar that was free energy of mixing. This will be X partial molar excess free energy of I. I can be A, I can be B. Okay, GI bar. What is this? This you know what is clear. What it says, GI bar here. This partial molar free energy is simply partial molar free energy. Likewise, this also partial molar free energy. The difference is it is real, ideal, subscripted. If the solution under study is real, then what it says that you get the partial molar free energy of the solution under study, which is real. And what is excess? Now, this real value, how much it is? It has deviated from GI bar